So in yesterday's class, we talked about the importance of solutions to chemists. Remember, a solution is when I have something called a solute dissolved in another medium, which is usually water, which is my solvent. So solutions for me as a chemist, I would say in my career, 99% of the time involve something being dissolved in water, and that is a solution. And yesterday we talked about how to make a solution by calculating how much mass of my dry powder I need to make my final solution, and then what volume I need. So if I know what volume I need, if I know what volume I need and what concentration I need, then I can basically calculate the number of moles using the number of moles is equal to mass divided by molar mass, or mass equals number of moles times molar mass, and I can figure out how much mass I need to weigh out. Okay, so it turns out that at Bernie Custis, in my storage room, I think I must have about 500 bottles of dry chemicals. And whenever I use one of those chemicals, I'd say for 475 of those 500, almost all, before I use it, I will dissolve it in water, and I will need to know how much mass I need to dissolve, in what volume, and then it will help me to calculate the concentration of the solution I've made. Okay, so every lab, right? As a chemist, remember the reason we dissolve our chemicals is so that I don't just have, remember I used the example of my body and my skin, whereas if my whole body was immersed in something, the only part of me that could react with the outside world would be my skin, right? But if my skin is really only maybe 3 or 4% of my entire body, the rest of me never gets access to what's outside of my body. So if I could take all of my body and basically find a way to chop me into little bits and then use all those little bits, I would have so much more of me that has access to the lab. And that's exactly what I want to do with my crystals. So if I have crystals of a chemical, okay, there's the crystal of, I don't know, sodium chloride, and I want it to react, but this crystal is made up of millions of molecules of sodium chloride, like a sugar cube, and the only part of this solid that can react is the part that is on the outside of the cube, right? All the stuff on the inside is protected from the outside world by what's on the surface. So we know that when I dissolve this in water, all of these molecules get separated and they float around in the water, and they all have the ability to react. So that's the idea here. I'm making a solution so that my chemical reaction can be much more efficient and it will work that much better. So yesterday we talked about making solutions by going to the chemical cupboard, picking up the jar of, here's my jar in my storage room, and this is my jar of sodium chloride. So I go to the storage room, I pick up my jar, I determine how many grams I'm going to put into my beaker, right? I'm going to pour the grams, I'm going to weigh them, I'm going to pour them in there, I'm going to add my water, and then like we were doing yesterday, the crystals are going to disappear, and I'm now going to have my solution, which is, undo. I'm going to have my NaCl, and remember from earlier in the course, one of our options for states of matter, solid, liquid, or gas, the fourth one was aqueous, which is something which is dissolved in water. In this case, my sodium chloride molecules are dissolved in the water, and they're floating around, and they have the ability to react. Okay, so there's my sodium chloride aqueous. Now it turns out that in my prep room, not all chemicals that I buy, of the 500 that are back there, some of them come as a liquid. When I buy them as a liquid, they come as a very concentrated liquid. Now, let's pretend we're in the kitchen for a minute, and let's imagine if I was cooking something, and the recipe called for a squeeze of lemon. So let's say I've got a big pot of something, maybe I've made a big, huge salad, right? And here's all my salad in here. And now it calls for a squeeze of lemon, and I take my lemon and I squeeze my lemon over the top here, and I get one squeeze. It's not very much, just a little bit of lemon juice in my salad, but now when I taste that salad, it tastes great. That lemon juice is there, and it really adds to the flavor. If I took the lemon and squeezed it directly into my mouth, it is very strong when it's on its own. But when I dilute it with all the flavors in the salad, it becomes much more useful for me as a cook. Right? Most people don't put pure lemon juice in their mouth, but lots of people put lemon juice in their salads, in their soups, in their chicken dishes, in their tea, right? All kinds of places where you put a tiny bit of this very strong flavor and you dilute it so it becomes more reasonable. Right? Same thing happens here. If I buy chemicals that come in a liquid format, they'll come in a jar, in a bottle, and this is concentrate. Right? This is called my stock solution. I store it in my stock room. Right? And the stock solution is very highly concentrated. So concentrated that it might even be dangerous. So I've got a bottle in the back room of hydrogen chloride. Okay? Now, it is pure hydrogen chloride. It is very, very strong. If I drop the bottle, it's a glass bottle. If I dropped it on the floor, we would have to evacuate the entire school. That's how strong the chemical is, right? Because what it would do was it would start immediately eating away at the floor tiles, creating gases which are not very good for anybody, and it would start eating a hole through the floor and dripping down into the room below us. Again, if it dripped on anybody, it would cause a very nasty burn. It's very corrosive. The pH, remember pH scale 0 to 14? The pH of this solution is less than 0. It's actually negative. So I buy this stuff because we use a lot of it. Now, in order to use this in my lab, what I'm going to do is very similar to what I did a minute ago, which is, so this is, HCl. I'm going to start with a graduated Erlenmeyer flask, and from here I'm going to take a very small amount, and put it in here. Just a few drops at the bottom, and then I'm going to add water, and I'm going to make it more dilute. I'm going to water it down. I'm going to make it more useful to me as a scientist. At this concentration here, it is really dangerous. At this concentration, it's perfect for the lab that I'm doing. So the question becomes, how many drops did I need to put in here before I added the water? And then how much water do I need to add so that it's the right concentration? So the concentration of this chemical here is much stronger than what I need. We do this all the time in cooking, right? If you're making pancakes, you'll go to the cupboard and you get out your vanilla, right? And you will put 2 drips of vanilla, 2 tiny little drips, drip, drip, and you've got enough vanilla to make the entire set of pancakes smell and taste like vanilla. Same thing with all of our different flavorings, right? So we buy things often as a stock. We buy it as a very concentrated solution so that we can use a little bit of it every time we need it. You think, well, why wouldn't I just buy this? Because I need so much of this solution that I would have to buy liters and liters and liters and liters and liters and liters. It makes more sense to buy the stock solution, 1 bottle, not even a big bottle, and then every time I need to have the chemical for a lab here, I'm just going to take a few drips out of here, add them to here, and then add the water, and now I'm ready to go. Next time I need to do a lab, I'll do the same thing. I will take my Erlenmeyer flask, I'll take a few drips from here, I'll put them at the bottom, and then I'll add my water, and I'll be ready to do a lab. And the next time I need to do a lab, you get the idea. So by having this stock bottle, I can make mega amounts of that chemical. And what I'm doing is I'm going to dilute my stock solution. I'm going to water it down. Okay, so 5.8. Chemists often buy chemicals as a concentrated solution, a very strong solution, and we call that solution our stock solution. Now, the reason why we do that is for two reasons. Number one, it's a lot cheaper to buy a small amount of a stock solution. I don't have to have huge storeroom for this chemical. One bottle will basically make me enough chemical for years, rather than filling my storeroom with liters and liters and liters and liters. So it's easier to buy a small amount of concentrate, and it's usually a lot cheaper to buy a small amount of concentrate. So I'm going to buy the concentrated solution or the stock solution, and then whenever I need to do a lab, I'm going to dilute it. I'm going to add it to water so that it gets to the concentration that I need. Now recognize that the stock will always be stronger than what I need. I can't start with a certain concentration and add water to it and make it stronger. That will never happen. Right? Whenever I add water to it, I'm going to water it down. I'm going to thin it out. I'm going to lower the concentration. So it says when we're doing a lab, we often need this lower concentration to do the lab. And because of that, we're going to dilute the stock solution. I'm going to water it down. So let's look at the strategy for watering this down, and we're going to look at our final formula here, which is this formula here. Now, let's look at how we're going to do this. So here's my stock solution, very concentrated. I'm going to call this solution 1. This is my stock. And then here is the solution I need for my lab today, right? This is solution 2, right? This is my diluted solution, right? So the formula up top here says if I know the concentration of stock 1, and I know the concentration that I need to do my lab. So let's say the stock 1 solution is 10 moles per liter. And that's very strong. And to do the lab, I need a solution which is 0.050 moles per liter. Right? This is really strong. This is dangerously strong, and this is perfect. So this is C1, it's the concentration of my stock solution, and this is C2, it's my concentration of my diluted solution. Now the other part of this says, how much of this do I need to use? What volume do I need of stock 1 to move into here? And then what volume of stock 2 of diluted solution am I going to get? Right? So V1 is the amount of stock that I'm going to use in milliliters, and V2 is the final volume of my solution, my diluted solution. And the formula for doing this calculation says C1V1 equals C2V2. Now, this is a nice, easy formula to rearrange, because we will be given always 3 pieces of information, and we'll just have to find the 4th one. The first information, usually what it's asking me to find is either C2 or V2. What concentration is my final solution, or what volume is my final solution? Right? And the answer will always pop out for us. So if I look at the sample problem on page 193, page 193, and it is sample problem 9. Question says, folic acid is one of the B vitamins. A pharmacy assistant, again, somebody who's been to college to learn how to work with a pharmacy, is asked to take the 0.1 mole per liter stock solution and to dilute it to make 0.0150 liters excuse me, of a 1 times 10 to the minus 2 mole per liter solution. Okay, so I'm going to draw my picture here. Here's my stock bottle, and here is the flask that I'm using as my pharmacy assistant. This is the stock, and this is my diluted solution. Okay. So what do I know? It says that the stock solution is 0.1000 moles per liter. That's the concentration of stock, 0.1000 moles per liter. You think that's not very strong for a stock? Yeah, but what we need is a much weaker concentration. It says I'm going to dilute it, and it says how much stock solution do I need? How much of this do I need? Now what am I going to make? I'm going to make a solution that's going to go into a patient's arm, right? I'm working at the hospital here, and this is a pregnant woman who needs a shot of folic acid. Right? The concentration that needs to go into her arm, this would really burn and sting, right? So I'm going to water it down so it's not as nasty. Okay, so the concentration that we're going to inject into her is 1.00 times 10 to the minus 2 moles per liter. That's given in the question. And it says the injection is volume 0.0150 liters. Okay, so remember this is solution 1, this is solution 2. It doesn't really matter which is 1 and which is 2, but I usually use stock as 1 and dilute as 2. So what that means is this concentration is C1, this volume is V1. This concentration is C2, this volume is V2. So now my formula says C1 times V1 equals C2 times V2. Now, my unknown here is V1, right? How much stock solution do I need to add? So here's my V1 here. How am I going to get V1 out of this equation? Well, I need to get rid of the C1 that's over here too. I need to get rid of this one. So to get rid of that one, I'm going to divide both sides by C1, right? Divide both sides by C1, and these two C1s will disappear, and I'll be left with V1 equals C2 V2 over C1. And I know C2, it's up here. I know V2, it's up here. I know C1, it's right here, and my unknown is V1, which is this one here. Now note the other way to do this. Let's get rid of this, and this, and this, 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 and this. So there's my original formula. C1 V1 equals C2 V2. Again, remember, if I'm trying to isolate V1 here, all I'm going to do is take my C1 from here down to the denominator on this side, and it will disappear. I move it to the other side on the denominator, in the denominator, and I end up with my formula. V1 is equal to C2 V2 divided by C1, right? C2 V2 over C1. So now I'm going to move up my screen here, and I'm going to substitute my numbers in. V1 equals C2, which was 1.00 times 10 to the negative 2. There's C2 times V2, which was 0.0150, divided by C1 here, which was 0.1000, and I'll end up with a final answer. V1 turns out to be 0.00150 liters. So what that's telling me, so there's my final answer. That's V1. So 0.00150 liters. If I go back to the top here, what that's telling me is if I take 0.00150 liters out of this bottle here, which is this concentration, and move it into here, I can add enough water to bring it up to this final volume, and when I do that, this will be the new concentration. Okay, that's what this formula is doing. So it's looking at how I'm making solutions again in the lab, except this time not using a powder, not using a solid chemical, but using a concentrated liquid chemical that I'm going to dilute in order to make my solutions for the lab. Okay, that being said, I'm going to leave you with these 4 questions here, questions 26 to 29 on page 193. I'm also going to leave you with the questions on page 197. So ignore this one for now. We'll come back to this next week when we do our Chapter 5 review. So right now I also want you to do the questions in the textbook, which are questions 5, 6, and 7 on page 197. Okay, so these questions here on 193, these questions here on 197. And we'll come back to the other questions tomorrow. These answers aren't in the answer set yet,